Hello, ladies and gentlemen. Can anybody hear and or see me?
Yep.
All right. Well, I hope you all had a great weekend and recovered from Halloween and the busyness of the weekend. I know how that goes. We only got one section today, section 5.1, as we begin a brand new chapter, ladies and gentlemen, as we're going to learn how to work with polynomials in chapter 5. Chapter 5 is entitled Exponents and Polynomials. And so we're going to show you how to eventually multiply polynomials together, divide them, add them, subtract them. And in chapter 6, then we'll get in probably to the heart of the entire course, which is learning how to factor polynomials, which is a critical survival skill for higher level math. Does anybody in here plan on maybe taking some more math in the future?
Yeah, I have 120 next semester.
Oh, okay.
Yeah, so do I.
All right. Well, that's great. You get to see more beautiful aspects of mathematics the higher you go. But yeah, factoring, the ability to factor polynomials is probably the most important chapter or skill you can get out of Math 082. So that'll be chapter 6. All right. And so in lieu of chapter 6, chapter 5 needs to be tackled here. All right. So section 5.1 is just going to warm us up to some properties of exponents. And we're going to start working with what are called monomials, which are one-term polynomial expressions. Okay. Now, I still have to post, and I do apologize, the lecture from October 27th, last Wednesday. And I do apologize for not having posted that. I will post that, immediately after class here. And I will, of course, update your homework. I know I updated the homework, but I will update it after this class. And also see if I can get the video posted for today. All right. Okay. So, ladies and gentlemen, let's begin section 5.1, working with basic rules of exponents. Okay. So 5.1 is entitled multiplication with exponents. And we're also going to touch base with something called scientific notation. Is anybody currently taking a science class?
Microbiology.
Microbiology. Okay. Well, scientific notation is used in microbiology because if you got the word micro in front of biology, that indicates that you might be working with things that are very small. Do you agree? Even too small to see with the naked eye. Am I correct in that regard?
Yeah.
Well, to represent very small sizes of things, ladies and gentlemen, or very large sizes of things, scientific notation is the way to go. As it is a very convenient way to represent extremely small numbers and extremely large numbers. So we'll look at scientific notation a little bit. And if any of you have to go onwards and take any course in science, chemistry or physics or physical science, or even in dosage calculation, scientific notation is something that you want to be somewhat familiar with, okay, as it is used quite a bit. All right. So the first thing we're going to open up with what are called rules of exponents, or sometimes these are referred to as properties of exponents. And we have worked with exponents a little bit in the past. For instance, okay, before I get into the rules of exponents, let's just warm up to what we know about exponents in general. Like if I give you this here, how would we read this expression? Anybody?
5 times 5.
Okay, well, we have 5
5
squared,
squared.
5 to the second power, which does mean you are correct. It does not mean 5 times 2. It means 5 times itself 2 times. So the exponent instructs us how many times we multiply the base by itself. And so this would evaluate to 25, correct? We've seen that. All right, just a little bit of trickery here. Anybody know what this evaluates to? I know I showed you this. It has been a while though. What does that evaluate to? Would this be positive or negative 16? Anybody?
Positive.
Positive.
All right. Uh-oh, I still have some takers on this. This is saying the opposite of 4 squared. So this is saying the opposite of 4 times 4, which is to say negative 16. Now, for those of you who think that was supposed to be negative 16, this is the one you want, okay? This, ladies and gentlemen, is going to be, excuse me, this will be positive 16, as this is going to be a negative 4 times a negative 4. Which will net us a positive 16. Remember, I know I warned everybody about this subtlety many weeks ago. In fact, it was probably months ago. Anybody remember that, those little differences there?
Yes.
Yeah, you got to be a little bit careful when you raise a negative to an even power, as we can get into trouble, okay? So notice this is saying the opposite of 4 squared, which is the opposite of 16, which is negative 16, but this is saying negative 4 squared, which is negative 4 times negative 4, which is a positive 16. All right, so this is an area of some concern in mathematics, as these seem like they're the same thing, but they are not. There is a subtle but very important, huge difference between these two expressions there. And so we have worked a little bit with exponents. Now we can begin to warm up with what are called formal rules of exponents here. And the first rule says that, ladies and gentlemen, when we multiply like bases together, and I'm going to use the same notation that your author's using in your textbook, because I know we all look at the sections that I go over or cover in the textbook. All right. What I don't like about the notation your author is using here, ladies and gentlemen, is that this looks like a what? Looks like an S, doesn't it? I mean, looks like a 5, doesn't it? It's supposed to be an S. So I don't know. I don't like the notation your author is using in your textbook. So I'm going to use this notation. When you multiply like bases together, you keep the base the same, and you are to add the exponents. Keep the base the same and add the exponents. Okay, that's what we're supposed to do here. So like this, apply this rule here for an example. Like if I got 2 to the 3rd power times like 2 to the 2nd power. All right, let's do this problem the long way first of all. What does it mean to multiply 2 by, or raise 2 to the 3rd power? Well, that means to take 2 and multiply it by itself, what, 3 times? Do you agree? Okay, so that's what that means. Now, what does it mean to raise 2 to the 2nd power? It means to multiply 2 by itself, what, 2 times. Now, what is 2 times 2 times 2 times 2 times 2? Well, 2 times 2 is 4, 4 times 2 is 8, 8 times 2 is 16, and 16 times 2 is 32. Everybody see that there? Well, there was an easier way we could have evaluated 2 cubed times 2 squared had we just tapped into this property here of exponents, okay? So we'll call this property number 1. And property number 1 says when you're multiplying like bases together, as we are multiplying like bases of 2 here, we keep the base the same, and then we raise it to the sum of the exponents. So we add these exponents together. And so therefore, this is really 2 to the what? 5th power, which is really saying 2 times itself 5 times. And if you had a basic calculator, you could raise 2 to the 5th power, and it would give you the result of 32. So you got to admit, 2 to the 5th power is a more compact way of representing 2 multiplied by itself 5 times. Do you agree? That's a real hassle. So this is much more compact and efficient to work with it in that sense there. Does that make sense to that first property? All right, let's look at another example. If I have x to the 8th power times x to the 24th power, what is this going to be equal to? Well, we keep the base the same, and what do I do with the exponents?
32.
We're going to add the exponents together, so 8 plus 24, hence we get x to the 32nd power, okay? So when you multiply like bases, you keep the base the same, and you add the exponents. Okay, that's what this property is telling us here. And this property also extends to more than one base. For instance, if you got 3 squared times 3 to the 4th power times 3 to the 8th power, this is going to be really equal to 3 to what power? Well, you add all these exponents up. So this is going to be 3 to the 2 plus 4 plus 8 power, which is 3 to the 14th power. Now, I'm not going to actually take the time to evaluate 3 to the 14th power because that would be a big number. And I would not expect you to do that, you know, in all honesty, without a calculator. But what I'm saying is you can rewrite this expression more compactly as 3 to the 14th power by making use of this property of exponents here. So any question about this first property of exponents and how it's helping us to multiply like bases together? All right, let's turn our attention to property number 2. So that's property number 1. And now we'll go to property number 2. Property number 2 says this: when you raise something to a power and then further raise it to some other power. So if you raise a power to a power, what are we to do with the exponents? We've seen what happened when you multiply like bases together, you add the exponents. What happens when you raise a power? What's that?
Would you multiply the exponents?
Yes. So what you do is you keep the base the same, and you're actually going to multiply these exponents together. So when you raise a power to a power, you multiply the exponents. When you multiply like bases, you add the exponents. Notice there's a difference here. A big word of caution here on this property. Some students think that when you raise a power to like a power, well, the first power gets raised to the second power. So some students think that this is really a to the m raised to the nth power. That, ladies and gentlemen, is not correct. Don't fall into this trap. Don't let that happen to you. This is not correct to say that when you raise a power to a power, the first power gets raised to the second power. That's not what this property is saying. This property is simply saying when you raise a power to a power, you just multiply the exponents. That's it. So be careful with that pitfall right here. Let's put this to the test. Let's see if this holds water. If I have like 2 squared raised to the 3rd power, okay? Let's work this out the long way and see how this property can help us compute it more efficiently. Do you agree that 2 squared cubed, so whatever's inside parentheses has to be cubed? Do you agree? How do you cube something? What does it mean to cube something? It means to take that something and multiply it by itself what? How many times?
3.
3
3
times.
times. So that means that this 2 squared is going to get multiplied by itself 3 times. So therefore, I'm going to have 2 squared times 2 squared times 2 squared. So that's what it means to cube 2 squared, is to have 2 cubed be multiplied by itself 3 times. Now, we just learned the property above. When you multiply like bases, you keep the base the same and you add the exponents. And when we add all these exponents, we really get 6. So as we're finding out, 2 squared cubed turns out to be 2 to the 6th. Well, we would have known that a little bit more efficiently had we tapped into rule number 2 here. That says that when you raise a power to a power, we keep the base the same and just multiply the exponents. We could have got to that 2 to the 6th more efficiently this way. You see that there? That's property number 2. When you raise a power to a power, you keep the base the same and you multiply you multiply the exponents. Does that make sense there? That's property number 2 there. Okay. Property number 2. All right. Let's try a couple practice problems to hone our skills on property number 2. We'll call that property number 2 there. Okay. We'll do a couple practice problems, and then I'll give you a classwork here. Okay, so here's some examples that illustrate the use of property number 2 there. If I have like 4 to the 5th power raised to the 6th power, this would be 4 raised to what power? When you raise a power to a power, you keep the base the same and you multiply the exponents. This would be 4 to the 30th power. Now, I don't want you to evaluate that because there's no way we're going to take 4 and multiply by itself 30 times without a calculator. That would be that would not be reasonable. Okay, this is going to be x cubed to the 5th power, and x cubed to the 5th power would simplify to x to the 3 times 5 power, or x to the 15th power. All righty. Does that make sense there? Okay. So those are some examples of using the first rule there. So what I'm going to do here is I'm going to give you some practice problems here. This will be classwork number 1. Now today is the first day of a new month, November 1st. I would like you to simplify each of these expressions for classwork number 1. Number 1, I want you to simplify x to the 14th power cubed. Number 2, I want you to try to raise b to the 2x power, and then I want you to cube b to the 2x power. Okay. Yeah. And number 3, let's see if you can do okay, that one there, that one. And let's see if you can do x to the 20th times x to the 14th times x. Problem number 4. See if you can take 2 raised to the 5th power raised to the x power. And number 5 here, if you got negative, let's see, negative 4 squared raised to the 9th power. Okay. All right. See if you can do those problems, ladies and gentlemen. That's called classwork number 1. We'll come back and
Is number 2 b squared?
number 2 is b to the 2x power raised to the 3rd power. Okay. B to the 2x power raised to the 3rd power. See if you can do something with that. All right, did anybody get the first one? What is x to the 14th to the third power simplified to?
X42.
Okay, when you raise a power to a power, you multiply these exponents. So 14 times 3 is 42. So it'll be x to the 42nd power. Number 2, when you raise a power to a power, you multiply the exponents. So 2x multiplied by 3 is going to give you, what do you think? 2x times 3.
B to the 6.
6x power. 2x times 3 is 6x. This was a little bit of a challenge one. I don't feel bad if you didn't get it. This one here, when you multiply like bases, you keep the base the same and you add the exponents. So it's going to be x to the 20 plus 14 plus what power here?
Was it 1?
1. Thank you. So it'll be x to the 35th power. Down here, raise a power to a power, multiply the exponents. This will be 2 to the, what do you think? 5 times x, 5x power. Again, don't feel bad if you didn't get it. This one here, ladies, don't anybody negotiate this one? Notice this negative sign is not inside the parentheses, so this is still going to be a negative. And then 4 squared to the 9th is going to be 4 to the 2 times 9 power. So it looks like this is going to be just negative 4 to the 18th power, the opposite of 4 to the 18th.
18th.
Yes. Did we get those correct so far? With the exception of maybe these. You doing okay out there in general?
Yeah.
All right. Let's look at property number 3. Property number 3 is kind of like a combination of the 2 other properties. So we'll call this property 3. And to show you how property 3 works, ladies, I'm going to start off with an example here. So I'm going to take 2x and raise it to the 3rd power. Now, what does it mean to raise something to the 3rd power? It means to take that something and multiply it by itself, what, 3 times? So do you agree this is really saying 2x times 2x times what? 2x? Which do you agree is really saying 2 times 2 times 2 times x times x times x if I just rearrange the factors? Do we agree with that? But do you agree 2 times 2 times 2 can be rewritten more compactly in what form? What exponential form?
2 to the 3rd.
2 to the 3rd power. And x times x times x can be written more conveniently as x to the 3rd power. Now, ladies and gentlemen, how can I go from 2x to the 3rd power to 2 cubed times x cubed more efficiently? Can anybody think of a rule that enables me to go from here to here? Can you see what's going on here? Can you think of a rule? Can you think of what our rule 3 is going to look like? Well, property number 3, it says this, ladies and gentlemen, in general, if I got the product of 2 or more factors inside parentheses raised to a power, I can raise each of these factors inside the parentheses to that power. So I can raise a to the mth power times b to the mth power. This is property number 3. Everybody see that there? So when you got 2 or more factors inside parentheses raised to a power, you can raise each of those factors inside parentheses to that power. Okay, that's property number 3 there. This is mth power there. So we could have followed that rule in raising this factor of 2 to the 3rd power times and raising this factor of x to the 3rd power to get here. That's property number 3. That's a legal property of exponents there. Okay, and so therefore, knowing that, let's see if we can do a couple of examples here in lieu of classwork number 2. Look at a couple examples. So if I got 3y squared, you agree by property 3, I can take each of these factors inside parentheses and raise them to the second power out here. So this can be rewritten as 3 raised to the second power times y raised also to the second power. See that there? And we can go on and simplify this even further if you want. 3 squared is 3 times 3 or 9. So this simplifies the 9y squared. Everybody see what happened there? Let's try another one here. What if I take negative 1/4 times x squared and I raise this to the second power? Let's try this example. So if I take this negative 1/4 x squared and square it, that's saying that everything inside the parentheses, every factor inside the parentheses has to be squared. Well, negative 1/4 is inside the parentheses, so that has to be raised to the second power times x squared is inside the parentheses, so that has to be raised to the second power. So that's the application of property or rule 3. But what does it mean to square negative 1/4? Well, that means to take negative 1/4 and multiply it by itself. And what is x squared squared? We learned that in property 2, when you raise a power to a power, you multiply the exponents. So this is going to be x to the 2 times 2 power, or x to the 4th power. Now a negative times a negative is a positive, and 1/4 times 1/4 is 1/16. 1/16 x to the 4th. And that's how that would simplify. Any questions about how I simplified that problem? Using property 3 from here to here. And then I used property 2 to go from here to here. Okay, so we're starting to tap into these properties here. Oh heck, let's go all out here. How about 2x squared y cubed, all raised to the 4th power? Let's see if we can simplify this or rewrite this in simplified form. Well, according to property number 3, everything inside the parentheses here, every factor inside the parentheses must be raised to the 4th power. That means this 2 must be raised to the 4th power times x squared must be raised to the 4th power times y to the 3rd power must be raised to the 4th power. What does it mean to raise 2 to the 4th power, ladies and gentlemen? Well, that's 2 times 2 times 2 times 2 times 2. 2 times 2 is 4. 4 times 2 is 8. 8 times 2 is 16. So this simplifies to 16. When you raise a power to a power, rule number 2 says we multiply the exponents. So this will be x to the 2 times 4 power, or x to the 8th power. And y to the 3rd power to the 4th power means, again, we multiply the exponents. So it'll be y to the 3 times 4 power, or y to the 12th power. And that would be your answer. We all understand how we got that answer there. Now I'm going to give ourselves a challenge problem to do. Do we have all these accounted for up here on this page yet? Anybody need to still see those? We okay? Slide it up, please. Here's a challenge problem. What if we have x squared, y to the 5th cubed times x to the 4th, y squared, and we got the square outside. We can't put the 2 outside there. So let me erase that there and fix this. That looks awful there. Erase that there. And see if I can put that exponent there. Okay, so this is going to be squared. All right, so ladies and gentlemen, everything inside the first set of parentheses has to be what, raised to the third power, correct? So that means this x squared has to be raised to the third power times y to the fifth inside the parentheses has to be raised to the third power times everything inside this set of parentheses must be raised to the second power. So y to the fourth must be raised to the second power. I'm sorry, x to the fourth must be raised to the second power. Times y, because this is times, so times, y must be raised to the second power. Everybody understand how I got to that step there? Just employing property number 3 on this and this to expand it out to this. Now we need to go further. Now we have to shift gears and go back to property number 2. What do we do with the exponents when we raise a power to a power? Anybody remember? Multiply them. So x squared cubed is going to be x to the 2 times 3 power, or x to the 6th power, times y to the 5th power raised to the 3rd power is y to the 5 times 3 power, or y to the 15th power, times x to the 4th power raised to the 2nd power is x to the 4 times 2 power, or x to the 8th power, times y to the 2nd power there. Do we understand how we got it down to this by applying rule 2 there to each of these? Are we done, ladies and gentlemen, or does anything else need to be done? What would be your guess? Is that simplified completely, or is there something else we need to do?
We need to add both x's.
We'll not add both x's, but we need to what?
The exponents.
We got to multiply like bases now, correct? Yeah, there's like bases that are in need of being multiplied together. So we need to take this x to the 6th and multiply by x to the 8th. I'm going to rearrange these factors here so I can get my x's adjacent to each other. It's legal to do this. No harm in doing this. And I'm going to get my y bases adjacent to each other. You can always rearrange bases. Okay, ladies and gentlemen, in a multiple product expression. Now we're going to go back to rule number 1, the first rule we opened up with. When you multiply like bases together, do we remember what to do with exponents? Add these exponents. So x to the 6th times x to the 8th is going to be x to the 6 plus 8 power, times y to the 15th multiplied by y to the 2nd is going to be y to the 15 plus 2 power. Hence our answer is going to be x to the 14th times y to the 17th power. And we're done. That would be your answer. We started here and I showed you all the steps to get down to our final simplified result there. Any questions about that problem? The key is practice, ladies and gentlemen. The more of these we practice, these rules are going to start to seem like second nature to us. I mean, we're going to be able to employ them and shift through them as easily as we take our next breath. Okay? Practice is the key. Practice is very important there. All right. And speaking of practice, maybe I could give you some classwork problems here. Classwork number 2. We'll call it classwork number 2. Any questions about any of these problems on this page here? Do we have these accounted for one way or another, either written them down or taken a picture of them? You got those? All right, these are excellent practice problems here. All right, we'll call this classwork number 2. Again, today is the first day of November. I can't believe it's November already. It's bizarre how fast September and October went. All right. I want you to try to simplify these expressions. Problem number 1 I want you to simplify 4x to the third power. And ladies, I'm going to actually simplify the number to a power down to what it should be. Okay, so take it full simplified form. Number 2, I want you to take 4a cubed b to the second, and I want you to raise this to the second power. See if you can simplify that. All right. How about a decimal? Now I know you know how to do the little basic decimal multiplication, so I don't think that this is going to be an issue. Take 0.4 AB squared, AB cubed, and I want you to square this entire expression. Please simplify this one all the way down. Number 4. I want you to try to simplify y squared cubed times y to the 4th raised to the 5th power. Simplify that one. Problem number 5. Okay, we already got one like that. All right. I want you to work with a basic fraction here. 2/3 a to the 4th, b to the 5th, and I want you to square that. All right. Ladies and gentlemen, we will call that classwork hold on a second here. Call this classwork number 2. One last problem is number 6. Give you a little bit of a challenge here. 2x squared y cubed times 3x y squared squared. See if you can simplify this all the way down. All right, we'll call that classwork number 2. I'll give you some time to work on this. Take your time and try to do a good job.
Maya.
All right, let's see if we can begin to wade into these and see if you had any success. Did anybody do number one here? Got an answer for number one?
64x to the third.
All right, 64x to the third power. Anybody else get that? 64 times x to the third power.
That's what I got.
This is going to be 4 cubed times x cubed. 4 to the third power is 64. And you'll have x cubed. That should be the answer. Okay, good. Number two, what would this simplify to? Anybody?
A to the 6, B to the 4.
All right, 4 to the second power. A to the third power raised to the second power is a to the 3 times 2 power, which is a to the 6 power. B to the second power to the second power is b to the 2 times 2 power, or b to the 4th power. You are correct. That would be the answer. Number 3. Anybody get an answer for this one? Rebecca, did you get an answer for number 3?
I got 0.16 a to the second power, b to the 6th power.
You are correct. Nice job. 0.16 a squared b to the 6th. That is correct. Number 4. Anybody want to try that one there? Liberty, you want to give it a shot? You get anything, Liberty?
Y to the 26th.
Okay, y to the 26th power. Let's see, when you raise a power to a power, you multiply these exponents. So that'd be y to the 2 times 3 power, y to the 6th power, times y to the 4th power raised to the 5th power is y to the 4 times 5, or y to the 20th power. When you multiply like bases, you add the exponents. You are correct. 6 plus 20 is 26. Y to the 26th. Nice job. Anybody want to try number 5?
I got 4 ninths, A to the 8th, B to the 10th.
Okay, that sounds good. 2/3 to the second power is 2/3 times 2/3, which is 4 ninths. A to the 4th power raised to the second power is a to the 4 times 2, or a to the 8th power. B to the 5th raised to the second power is b to the 5 times 2, or b to the 10th power. That is correct. Nice job. And then the grand finale problem here. Number 6 there. Let's see if I can, let's see, Blanche, did you do anything with the last problem? You got anything here?
I was starting to look at it, but no.
All right. I admire your honesty. Cheyenne, did you do anything with that last problem?
No, I didn't start it either.
Nothing there. Monique, did you try anything, Monique?
Nope.
Let's see here. Who else here? Jennifer Miller, did you try anything with this last problem?
No.
No. Let's see. China, did you try anything with this last problem?
I got up into 4x to the 4th power, y to the 3rd power times 9. Wait a minute.
All right.
Times 9. And then x to the 2nd power, y to the 4th.
You're on the right track. You're definitely moving in the right area, right direction there. All right.
I got 72 x.
That's where I stopped at.
to the
That's not
second.
like my actual.
Okay. Okay. Yeah, no, I understand that. You were moving in the right direction, though. You're definitely going in the right direction. All right, well, we can, let's just take a look at that. And, oh, by the way, who said 72? Go ahead and finish with your answer.
I said 72 x to the 8th power, y to the 7th power.
Y to the 7th power, okay. All right, let's see if that works out here. That looks like it has some promise. Now we have everything inside the first parentheses gets cubed, so 2 to the 3rd power. X squared gets cubed. Y gets cubed. Times everything inside the second set of parentheses gets squared. 3 gets squared. X gets squared. Y squared gets squared. All right, now 2 to the 3rd power is 2 times 2 times 2, which is 8. When you raise a power to a power, you multiply the exponent. So x squared cubed, as it turns out, is going to be x to the 2 times 3 power, or x to the 6th power, times y cubed, times 3 squared is 3 times 3, or 9. This is x squared. Y to the 2nd power squared is y to the 2 times 2 power, or y to the 4th power. All right, we
Okay,
got it.
I
What's
messed
that?
up. Cause I see where I messed up in the beginning. I
Mhm.
squared my 2 and x instead of like raising it to the 3rd power.
Oh, okay. You thought this squared pertained to the 2 and the x?
Yeah, I kept it x squared.
Only x is squared, 2 is not squared, but everything inside the parentheses has to be cubed. 2 has to be cubed, x squared has to be cubed, y has to be cubed. Okay, so that's why I got what I have there.
Okay.
Now, we can rearrange these factors here if you want to get them adjacent to each other. It's perfectly legal to rearrange these factors. So I'm just doing that. So 8 times 9 is 72. X to the 6th power times x to the 2nd power is x to the 6th. When you multiply like bases together, you add the exponents. So 6 plus 2 is 8. So x to the 8th power. Y to the 3rd power times y to the 4th power is y to the 3 plus 4 power, or y to the 7th power. And you know what? Whoever read me this answer off, you were right on the money. You got that correct. Nice job. You were correct. All right, ladies and gentlemen, so we've learned some rules of exponents in this section here. We learned 3 rules. First one says when you multiply like bases, you add exponents. Second rule, when you raise a power to a power, you multiply exponents. And the third rule says any number of factors inside parentheses raised to the mth power has each factor being raised to the mth power inside the parentheses. Okay. Now, there's only one other thing that really concerns us in this section here, and that would be working with what are called exponents a little bit, or actually warming up to not exponents, excuse me, scientific notation. Scientific notation, okay? All right, scientific notation is a nice way to represent large or small numbers. Nice way to represent large or small numbers. And scientific notation form has this form here. This is called scientific notation form. Now, this looks like an X, ladies and gentlemen. That's not an X. That means that's literally the multiplication symbol from basic math. That means times. You see this number A here? This number A has to come from this list. This number A has to be either a 1 or a 2 or a 3 or a 4 or a 5 or a 6 or a 7 or an 8 or a 9. So this number A here has to be either a 1, 2, 3, 4, 5, 6, 7, 8, or 9. It cannot be 0. 0 is not in this list. It cannot be 10 or 11 or 12 or 25 or 30 because none of those numbers are in this list. This is called strict scientific notation form. N is called the exponent. All right. And so this is a convenient way to represent very big or very small numbers. And since, ladies and gentlemen, we have not learned negative exponents yet, there do exist negative exponents. We haven't learned about any of those yet. We can only talk about very large numbers today. We cannot talk about real small numbers. Okay. So we'll talk about only large numbers today. Let's see. Here telling that I think the richest person in the United States right now, the last figure I seen, the person had $300 billion or was worth 300 billion bucks. I'm not going to use any names, but ladies and gentlemen, how would we write the number 300 billion in what's called expanded form? Expanded form. Oh, by the way, it's not me, if you're thinking. It's not me. Expanded form, 300 billion. How do we write it? 300 with how many zeros? 300 billion. Anybody? How many zeros for a billion?
6.
No, 6 zeros is millions. Pithy millions.
9.
9.
9. All right, so yeah, one fella has $300 billion, is worth 300 billion. All right, somebody's worth that amount. Now, ladies and gentlemen, that's a big number, isn't it? All right, that's a pretty big number, and I hope you all get to experience that number in your bank account someday. Yeah, that's happening. But anyways, $300 billion, ladies and gentlemen. Now, notice I did put commas in here so that we could read the number more conveniently. But when we use scientific notation, ladies and gentlemen, we got to be careful with commas because commas can look like decimal points. So that is 300 billion. Let's get rid of these commas here. I don't want them to, you to be confused, thinking that they might be like decimal points. So I'm just going to, vanquish those things there. How would I write this 300 billion, which presently is written in expanded form? How would I write this number in scientific notation form? Well, this is a big number here. As I'm going to write this in equivalent scientific notation form, we got to ask ourselves where we would place our decimal point. I have a question for you. I don't see any decimal point in this number. Where is my decimal point understood to be? Where's my decimal point?
Is it behind the 0?
Behind which zero? There's a lot of zeros here.
Oh, the last one.
Oh, the last zero. Yeah, you are correct. The decimal point, even though we don't see it, if this is 300 billion, the decimal point's understood to be right there behind that last zero. Because this is the ones place, tens, hundreds, thousands, 10,000s, 100,000s, millions, 10 millions, 100 millions, billions, 10 billions, 100 billions, 300 billion. You see that there? Okay, we're going to put this number into scientific notation form. But the big question is, the billion-dollar question here, no pun intended, is where do we put our, where do we place our decimal point to ensure that the number to the left of the decimal point, ladies and gentlemen, has to be strictly either a 1, a 2, 3, 4, 5, 6, 7, 8, or 9. Let me ask you this. If I put my decimal point right here, would that be correct? You wouldn't want to put the decimal point here because to the left of the decimal point is the number 300. 300 is not in our list here. You don't put it here because to the left of our decimal point would be the number 30. 30 is not in this list here. You don't put the decimal point right here. If you put the decimal point here, it's understood there would be a 0 to the left of the decimal point. 0 is not in this list. Where do I put my decimal point?
Behind the 3.
Oh, behind the 3. So right here, correct? Now, let's count how many places we have to move our decimal point to get it between the 3 and the 0. Here we go. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and what? 11 places? And so, ladies and gentlemen, this would be 3 times 10 to the 11th power. That is in scientific notation form. 3 times 10 to the 11th power means 300 billion. Everybody see that there? Because my decimal point in scientific notation is understood to be right here. And to the left of the decimal point is the digit 3. And 3 is in my list here. You see that? 3 times 10 to the 11th. Why did I put 11 up here again? Where did this 11 come from? I forgot.
How many places you had to move the decimal point?
How many places I had to move my decimal point to put it between the 3 and the 0. I had to shift it to the left 11 places to get it here between the 3 and the 0. That's why it's times 10 to the 11th power. Notice my exponent's positive. Positive exponents suggest big numbers. Negative exponents, which we will start to talk about negative exponents later on. Negative exponents represent small numbers. Numbers of sizes of things like in microbiology that you cannot even see with the naked eye. I don't think you can see the COVID virus with your naked eye, can you? The COVID virus? Not with the naked eye. In fact, they probably have to use an electron microscope, ladies and gentlemen, to see something so small. It boggles the mind when you think that something so small that you cannot even see with the naked eye is enough to floor us. Do you agree? That's a scary thought. It's a wonder we live as long as we do. 300 billion, ladies and gentlemen, is 3 times 10 to the 11th power. Now, you don't have to put a plus sign on the exponent here. It's understood the exponent's positive. I'm going to get rid of that there. Okay, so that's a big number. Let's try another one here.
So is that decimal necessary?
No, this decimal after the 3 in scientific notation is not even necessary either. Don't need it. It's understood. It's right there. Understood. Okay, thank you for bringing that up. Let's try another one. Let's see here. The sun, which is the closest star to our planet, ladies and gentlemen, the sun that we're starting to lose here as we dive into winter, is about 93 million miles away from our planet. 93 million. How many zeros do I put to the right of this 93 to have 93 million? 6. 1, 2, 3, 4, 5, 6. That's how far away our sun is from the earth, about 93 million miles away. And it's a good thing it is, otherwise we would literally burn up because our sun is colossal in size to our planet Earth. Our sun could engulf hundreds or even thousands of our planets. That's how big the sun is, ladies and gentlemen. but it seems small because it's 93 million miles away. Okay, now help me write this number in scientific notation form. Notice the decimal point currently is understood to be right here. We call this number here in expanded form. Oh, I don't need to write that. I got it up here. All these are in expanded form. We're going from expanded to scientific notation form. Where do I have to put my decimal point to force this to be in scientific notation form?
After the 9.
After the 9, right here, after the 9?
No, between the 9 and the 3.
Between the 9 and the 3. You're right. The decimal point has no choice but to go right here. You can't move it here. If you put the decimal point here, then you got 93. That's to the left of the decimal point. 93 is not a number in our list. It can't go right here in front of the 9 because to the left of the decimal point would be understood to be a 0. There's no 0 in our list. It has to go between the 9 and the 3. So that to the left of the decimal point, we have the number 9. 9 is right here in our list. So it has to go here. How many places to get it there? Here we go. 1, 2, 3, 4, 5, 6, 7 places. And because I moved my decimal point 7 places in scientific notation form, the exponent on 10 will be what? 7, agree? Because I moved my decimal point 7 places. So it's going to be 9.3 times 10 to the 7th power. Ladies and gentlemen, this represents the number 93 million miles in this case. So that's 93 million in scientific notation form. 9.3 times 10 to the 7th power. Is this making sense here how we're doing this?
Yeah.
All right. So here's what I want you to do for classwork number 3. Classwork number 3. I want you to write these numbers in scientific notation form. All right, here we go with some numbers. Okay, how about 5? Put that in scientific notation form. That'll be problem number 1. Problem number 2, try this one. Put that in scientific notation form. Problem number 3. Put that number in scientific notation form. Okay, go ahead and do those. I'll give you a couple minutes. Classwork number 3. Problem number 1, anybody write that in scientific notation form? Number 1.
Is it 5.x?
Time
Times-
5 times 10 to
Yeah,
the what
5 times
power?
10 to the 20th.
5 times 10 to the 20th power?
Yep.
You are correct. You don't actually have to put the decimal point there. It's understood it's there. So just say 5 times 10 to the 20th power. Okay.
But you do have to put it for 2 and 3, right?
Yeah, we do for 2. Let's see if I can get somebody else to answer number 2. Julian, did you do number 2? Number 2, Julian. How about Kaylin McPhilmy? Did you do number 2? I don't know. China, did you try number 2?
Yeah, I tried it.
What'd you get? Tell me what you got.
I got, well, I came up with, is it 1.63 times 10 to the 13th?
Boy, that sounds pretty promising. You know, you got it right. 1.63, nice job, times 10 to the 13th power. Anybody else get that?
Yes.
Big number, huh? All right, last one. Who wants to give it a shot? Number 3, how do we write that in scientific notation form?
I got 9.934 10 times 10 to the 8th power. Or I think I got 18th power. I'm sorry.
Oh, okay. I was gonna say
Yeah,
8 power, yeah.
I
All
wrote
right,
that down wrong, but I meant 18. Sorry.
you are correct. Nice job. All right, ladies and gentlemen, these are big numbers, aren't they? These are huge numbers. You know, I think this number up here even exceeds our national debt, doesn't it?
Probably.
Yeah,
I'm more than sure.
I I sincerely hope so, because I cannot afford to pay that off. I don't know about you, but all right. So questions how we're going from expanded form to scientific notation form. I have a question. You think we should be able to go backwards from scientific notation form back to expanded form? I don't see why not. Let's see if we can go backwards on a couple of numbers. Suppose I give ourselves this number here, 2.35 times 10 to the 7th power. How would I write this number back in expanded form? Well, I have to move my decimal point. So how many places to the right?
7.
10 places? How many places to the right do I move my decimal point? 10 places?
7.
7 places to the right. So here we go. We're going to have our 2.35 and we got to move it 7 places to the right. So 1, 2, 3, got to add a 0, 4, add another 0, 5, 6, 7. There you go. And then you can get rid of your decimal point. So you might want to do this in pencil so you can erase your decimal point. That's what the number would be in expanded form. Anybody want to read that number to us? How do we read it? How do we read this number?
23,500,000.
You are correct. 23,500,000. All right, nice job. All right, let's try another one here. Let's see, 1.6 times 10 to the 15th power. 1.6 times 10 to the 15th power. Let's write that in expanded form. So I'm gonna have to shift my decimal point. How many places to the right?
15.
15. So there's 1 place, and that means I gotta what? Have 14 more zeros? Do you agree? 1 place, and I got 14 more places to go. So that means 14 zeros now. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. And the decimal point would be right there. That would be 15 places to the right. And then please erase this once you get done placing your Oh, your zeros there. And that would be your answer. I don't even know if we can read this number. This number might be too big. I mean, what is this here? There's the thousands, there's the millions, here's the billions, here's the trillions, 10 trillions, 100 trillions. What comes after trillions? Is there a name for a number after trillions? Trillions. Ooh, I'm not sure.
Quadrillion is possibly.
What is it?
I think quadrillion, but I'm not sure if that's the actual number.
Yeah, I'm not sure. I honestly don't know myself. I know all the way up to trillions, but I'm not sure what the next largest denomination is called beyond trillions, as far as the name is concerned. So this is a
I
big,
remember hearing once that after trillion, it was like kind of impossible to
just a big number, correct?
count.
We just call
So
it a
is that
big
true?
number.
Like you really couldn't count after that. Yeah, so I guess that's kind of why.
Yeah, I don't
after
know
the
if it,
government said we were in trillions of debt, it was kind of
Yeah.
was like them kind of saying, we're kind of past,
Yeah.
being a point of payback after that.
Yeah. Yeah, I don't know what the name is beyond trillions. There probably is a name, but I honestly don't know what it is. It escapes my mind at this time. But there are numbers bigger than trillions, ladies and gentlemen. There's numbers that are astronomical, literally astronomical. I mean, there's some stars out there. There are some stars, ladies and gentlemen, that are so far away from our planet. Some of them are like hundreds of thousands of light years away. What's a light year? 1 light year is the distance. It's the distance that light would travel in 1 year. And the speed of light is pretty fast. Does anybody know what the speed of light is? What is the speed of light? Light's pretty fast. Anybody got a phone? Ask yourself the speed of light in miles per hour. Go ahead. Anybody ask your phone? You got a phone out there. What's the speed of light?
I don't have the answer to that one, but after trillion, it's quadrillion.
Quadrillion. Okay, thank you. So here we go. There's the millions. There's the billions. Here's the trillions. That's 1 trillion, 10 trillion, 100 trillion. And so this would be one. You said what, quadrillion?
Yep.
Yeah. So this would be one quadrillion, 600 trillion. That would make the richest person on the planet look like a pauper. Do you agree? Literally a pauper. All right. Unreal. This is a big number. Yeah, 1 quadrillion, $600 trillion. If you had that amount of money in your account, would you be doing this right now, ladies and gentlemen? Never say never. You might be bored with life. Do you agree, having all that money? All right. Let's see here. Let's see if we can. Oh, here's something interesting. This says, this is problem 88 in section 5.1. It says, if your pulse is 72, then in 1 year, your heart will beat at least 3.78 times 10 to the 7th times. 3.78 times 10 to the 7th times. So if your pulse rate is 72, like your heart beats 72 beats per minute, in 1 year, ladies and gentlemen, your heart will beat this many times in 1 year. In 1 year. That's amazing. I mean, the heart is really a mind-boggling organ of the human body. It really is incredible when you think about it, how durable it is. Let's turn this into expanded form. So I move my desk point 7 places to the right. So that's going to be 1, 2, and then I got to add 5 zeros. So this will be 3, 7, 8, 1, 2, 3, 4, 5. That's how many times your heart will beat in 1 year if your pulse rate, we're assuming a 72 beats per minute. So that would be how many times here? This is, that's what, 37,800,000 times? 37,800,000 times in 1 year. That's how many times your heart beats in just 1 year. That's incredible that the heart is that durable that somebody can live, to an age of maybe 80 or 90. I just find that, extraordinary to even ponder. It's amazing the heart is that durable. So take good care of your heart, ladies and gentlemen. It is obviously a pretty hard-working organ in your body. All right. Let's see what else we got here. If you're alive, if you've been alive for 21 years, then ladies and gentlemen, you've been alive for 6.5 times. You ready for this? Times 10 to the 8th seconds. If you've been alive for 21 years and you have been alive for this many seconds, let's put this into standard notation. So we move the decimal point 8 places to the right. So that's 1. And then we got to go 7 more, add 7 zeros. So 6, 5, 1, 2, 3, 4, 5, 6, 7. So if you've been alive for 21 years, then you've been alive for how many seconds? Well, how do you read this here? 650 million seconds. You've been alive for 650 million seconds if you've been alive for 21 years. All righty. That's incredible. All right, classwork number 4. This is the last classwork, ladies. I'm going to enjoy this one. I want you to write these. Hold on a second here. We did classwork 3, didn't we? Yeah, we did. Yeah, okay. I want you to write these, ladies. I'm going to write in expanded form or normal decimal form, as they call it. All right. 5.2 times 10 to the 6th. Problem number 1. Problem number 2. 1 times 10 to the 12th power. All right, just see if you can do those. I'll give you a minute or so, then we'll wrap this class up. Okay. All right, ladies and gentlemen, 5.2 times 10 to the 6th power. That means we move our decimal point 6 places to the right. So 1, and then we got to add 5 zeros. So this be 5, 2, 1, 2, 3, 4, 5. Did everybody get this answer? 5,200,000.
Yes. Yeah.
This one here is decimal points understood to be right here. So we just got to move it 12 places to the right. It means you add 12 zeros. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And so this is going to be, let's see here. This is millions. This is what, billions. This is what? 1 trillion? 1 times 10 to the 12th is 1 trillion. Make sense? All right. I think we're good for tonight, ladies and gentlemen. I think we've talked about enough out of 5-1. So we learned some rules of exponents, 3 rules, and then we learned how to work a little bit with scientific notation involving big numbers, large numbers. In the future, we'll learn how to work with scientific notation involving small numbers, okay? But that involves negative exponents. We haven't talked about negative exponents yet. We will get there. So unless there's any other questions, I will let you go. You have a great night, okay? And stay warm and stay safe.